Good morning. Good morning. So yeah, thank you, Jed. As Jed said, we're basically going to take a quick look at some tips, tricks, and hacks that you normally use on the web, but as viewed from within WebKit, right? So this is kind of a culmination of a lot of discussions we've had with people over the past few years, where we've noticed that they're doing certain things and realizing maybe like that the engine can kind of do different modes depending on like what kind of little tips they use. But we realized that a lot of people don't quite realize what's happening inside the engine when they do that, sometimes to bad effects or sometimes to good effects. So it's basically a talk where we can take a few of the really popular ones that we've seen where people seem to have a lot of misconceptions or misunderstandings of what's going on inside of the engine, and we're going to look into them to actually show you what is going on. Right, so, so Jed gave a little introduction. So again, I'm Matt, and this is Jing. And so we just left Apple early this year and are starting our own little company together in the Bay Area. So if you see us around, you can talk to us later more about that. But we basically worked together on the Safari and WebKit team for the past few years. Yeah, that's a bit about us. So, so to start off, there are basically a few demos that we had made to kind of illustrate the points of what these tips, tricks, and hacks are that people use. But we realize demos are kind of boring, right? Because if we could have synergy in our talk or whatever, right? Then that'd be great because everyone loves synergy. So like, let's make a game out of these tips, tricks, and hacks. Let's put them all together in like one example that's fun to do. So basically, last night we were kind of scrambling to do all this and fit it all into one. So we came up with a little simple game that we like to call Vertifall. And so a little play off the German word Wörter, which means words in German. The simple game that we made was essentially, you might be, you see like these words falling from the top of the page, right? So maybe like chocolate, cupcakes, whatever. And your objective for the game is to go through and type the words as fast as you can. So for every one that you type and you get right, you get some points for that, right? So if you type cupcakes really fast before it hits the bottom of the page and disappears, then you get like 8 points or so. And so on, and you're kind of just, going against the clock to see how fast you can type all the words. So that was a little fun little example that kind of brings together all of our all the things we want to talk about, and so we'll show you in a second what that game looks like. Basically, it's about like 2 a.m. last night, right? And we're totally freaking out because we need to get this all done before tomorrow. So we know that like there's only one way we can possibly get this done in time because we need to meet Malte, right, at the super awesome Raver Club at like 5 in the morning he's talking about. So it's like, it's game time, right? We have 2 a.m. until 5 a.m. to get this done, and then we have all this like super partying at the club until 9 in the morning, and then breakfast now. And if you have any clue, this is why we're so tired right now. This is a true story. So there's only one way we could possibly do this in time, right? So we know we need to get to Ballmer's Peak, right? So so to illustrate such a thing, we're going to do that right now as we go through.
All right, cheers.
This is a true story. OK, so this game that we're saying, right, the words are falling from the sky as they should be, right? And we're trying to type them as fast as possible. However, we get the game done, and all of a sudden it's not working, of course, because we're total noobs. And so the very issue we run into, the very first issue we see is that, is that all the words
are not there.
are not there, right? They should be basically flowing down from the top because we have a little transition that's like, going from the top to the bottom and sliding them down. However, it's not working. They like are stuck somewhere, right? So we go to look at the code for a second. And Jing will explain what we're doing here.
All right, so basically in our code, we have these divs that have classes word. And what we want to do is start them off at the top of the page, above the top of the page, and then have them animate all the way to the bottom. So what we did here was basically call this function called dispatch word that creates a word element, inserts it into the DOM, and then changes the top position to the height of the screen. So we were thinking about this last night, and we're like, oh, wait, weren't people on the web saying something about like you need to set timeout 0 between like inserting something into the DOM and changing its property, or else like the transition doesn't take effect or something? So we're like, OK, let's try this. We changed our code to basically do a set timeout 0 and then set the final top position. And then we're like, OK, let's try this out, see if it works. And it does. Woo. OK. So our game works. We're well on our way to partying. And we're also making our way steadily up Bomber's Peak, which means we got super distracted. So we're like, why do we even need a setTimeout 0? I mean, we have like one CSS value, the next one. Why can't the browser just do it? So we went online, and we looked up the definition of how transitions are triggered in the spec. So the W3C spec says when the computed value of a property changes, then the engine starts the transition. So we know a little bit about how web browsers work. So when you're running your JavaScript code, each chunk of your code is actually run in a single run loop inside the browser. And the browser kind of like manages when to call these run loops. And in between these run loops, then the browser does like whatever it needs to do to actually render your page, respond to system events, and anything that's not directly in your control. So one of the things that the browser does during this time between each run loop is to update all the styles you've set and layout. So that makes sense, because when we have a setTimeout 0, we're basically saying we're done with the first run loop, do whatever you need to do in the browser, and then do whatever we said later. So that's why it works. Awesome. OK, so we're done with that, and we're like, OK, we want to go party, we want to go party. Let's try playing this game. Huh. There's like this weird stutter when I type.
Yeah, so this is junk, right? This is too slow.
Bleh.
For some reason, every time we're pressing one letter, it's just absolutely slowing down. So this is not good either, right?
Nope. All right. So I know that the animation works fine, and it only slows down when I'm typing. So it must be something wrong with my event handler. So I go look at my event handling code, and this is the function I call. Basically, every time you type a letter, I loop through all of the word elements in the page, and then compare their inner text to see if it matches the letter typed. And if it does, then I'll just like change the class name, which sets some styles on it that highlights it. So as I'm looking at this, I start remembering there's this talk on YouTube. Oh, it's Paul Irish's talk about how accessing some values in the loop could cause reflows and slow things down. Actually, now I really remember it. It's inner text is one of these properties that causes a reflow. So I think the tip was to access all of your values at the same time, and then set your values at the same time. So I changed my code, and now I'm running two loops. The first loop gets all of the inner text, and the second loop just accesses a local variable instead of asking for it from the element. So let's run that code. Yay. Now it's responsive.
So breaking out that pattern so that we do all the gets of the inner text and then all the sets after, right? Then we're avoiding all of those reflows. So now we see it's much smoother, right? So of course, yet again.
So yet again, since Matt's still holding that beer, we're nearly atop Bomber's Peak, and we're like, why are we causing these reflows? I'm just asking for some text from the DOM. So we decided to actually just step through this loop and look at what's actually happening in WebKit's C++ code. So I put a breakpoint inside inner text, and this is the function that I see. And you see that the first line there says, call on the document, update layout, ignore pending style sheets. Super long name. So I'm like, what does this thing actually do? And then I kept stepping through. I'll save you guys all the pain of stepping through like 20 files. But at the end, it comes down to calling recalc style on the document. So I go into recalc style, and this is like this huge function that's like 3 pages long. And it does what it says it does. It recalculates the style if it needs to be recalculated. But the most interesting part is that near the end of it, the element actually loops through all of its children. And it says, if any of my children needs its style recalculated, then I also had to recalculate my style even if I didn't change. So I'm going through this loop, asking for inner text, and going through all of this logic. But I haven't changed anything, so this doesn't really trigger anything. OK, let's see what I did next. So the next thing I did is I changed the class name to something else. So again, I go into WebKit, and I see that this function called class attribute changed got called. And it does a whole bunch of stuff it's supposed to do. But at the very, very end, it says set needs style recalc. which sounds like it might trigger the thing we just saw earlier. So to help me organize my thoughts, I kind of graphed out what my DOM looks like. So I had the root document element, and then I had this game container that contains a whole bunch of words. And I just went through the first word and set its style. So the first word has a dirty bit for if the style needs to be recalculated. So now that I'm on to the next iteration of my loop, I'm looking at the second word. And I'm asking the second word for its inner text. And as you saw earlier, when you ask for inner text, it triggers all these function calls that go to recalc style. So the document asks, do I need to recalculate my styles? And it's like, oh, do my children need to recalculate their styles? And the game says, do my children need to recalculate their styles? And the first word says, hey, I need my style recalculated. So the first word does its own layout calculation things. And it goes back to the game, and the game says, well, one of my children had his style recalculated, so I guess I had to recalculate my style too. So what this actually caused in my game was that every single time I asked for inner text, the game element was relaying out all of its words. So if I had n words, I would have n loops, and inside each loop, I will relay out n words. So it's like exponentially expensive to have the accesses in the same loop as the setters. So that explains why I need to access all the values first, and then set all the values. So now
right, so
our game is pretty much done. What do you think?
Actually, to cap that point there for a second, you might ask yourself, like why does like the browser have to do all this work? Why can't it be as smart as my JavaScript loop could be, just to like cache those values essentially? And that would get into a big discussion of like, if you look at the way like style resolution and everything works inside of the browser, it's obviously a lot of really complicated CSS rules all implemented, right? So there are definitely some places where we can do that sort of thing, where we can speed things up. But at the end of the day, like we don't really know like what you're going to do next in JavaScript, right? So a lot of cases where it's just not worth it to possibly save around like every intermediary value between it. So basically, the take-home message there is like you just kind of have to accept the fact that like this is the current code, so this is what you have to deal with on the platform, right? So even the best things that can be done in the future, they currently don't exist. So it's just limitation of the current implementation, basically. But yeah, okay. So we fixed that, right? And we've understood that one. But now like we're looking at it, and if you can see, like keg is kind of just shaking as it's falling down. It doesn't really look that smooth, right? And since the perfectionists that we are, we want this game to be really, really smooth, right? So we remember this. We remember this tip that someone told us before, right? That was like use like translateZ 0 on elements when you're animating them, because that like sets hardware acceleration to happen or some such thing, right? So you can get these awesome crisp animations. So we recall this, and we're basically we go to use this little hack because this sounds great, right? So it boils down to before we had a WebKit transition, on top, so that it goes from top at 0 all the way down to the height of the page. But instead now we just added a WebKit transform with the translateZ initially 0, and then later we add translateZ and translateY, so it goes down the page. So same exact effect, just using transforms now as opposed to using a transition on the top. And this is the trick that everyone uses that should hopefully like hardware accelerate my animation, right? So let's check it out. Let's see if it works. Yeah, so that's buttery smooth, right? So this is the effect that everyone goes for, and it's like the holy grail of making awesome animations, right? You can't live without this if you're trying to do this sort of thing, it seems. But why doesn't like the browser do this on its own, right? Like we're curious, like what's going on here? So at this point, of course, we're totally like a top Balmer peak, right? We are even like jumping over the top of it, high-fiving, right? We are so curious about what goes on in the engine, and so we start to ask the questions, right? Like, why doesn't the browser always do this? Why don't I just always do it in my page? Like every animation I do, why don't I just add like translateZ 0? Because that would just make everything better, right? Well, not so fast, right? So we start by looking into the engine and seeing like what's going on when our curiosity is getting the better of us here. And we realize that there's some machinery being set up. We're now entering this thing called like compositing mode, right? So WebKit's dropping into this code that it wasn't in the case before when we were transitioning just on the top element. And so So it seems to be entering this compositing mode where it's setting up all this machinery, right? It's creating these like layer things, and you see a lot of code paths that are now being used that are like if-dep between accelerated compositing flags there. So what is compositing? What is this accelerated notion? Where's that hardware acceleration coming into play? And whatever happened to like talking about hardware accelerated rendering? So to understand all these concepts, we need to quickly just do a little segue to give a graphics 101 to understand this concept of what's going on with accelerated compositing. So in the next 5+ minutes, I'm going to try to fly through rendering from top to bottom as to how it works, especially in the lens of how it works in a rendering engine such as WebKit. And hopefully, I trick you into understanding how accelerated compositing works, all within breakneck time. So let's start. So compositing and rendering are the two different terms we're talking about here, right? Normally you hear people talking about accelerated rendering, but what does that mean? Well, rendering is the overall process of what we're doing here, where compositing is a substep of it. So we have to know what rendering is first so we can talk about compositing. So as it's defined, rendering is generally the process of taking a model and rendering it into an image. So by an image, I mean like, a bitmap image or, an actual like 2D array of pixels, just a little chunk of memory in the end, right? And your model, in the case of WebKit, and a rendering engine for the browser, right, is just basically your DOM plus CSS. So your model is simply that DOM that you give us in the CSS, and WebKit does the job of simply taking that and translating that literally into an image, right? And at the end of the day, I'm going to grossly oversimplify this, but let's say that image at the end is just called a frame. We'll just use that term for a second, and we'll say that once we've generated that frame, all we need to do is give it to the GPU, and my computer graphics friends are totally going to kill me for oversimplifying this so much. But let's just say that simply the job of the GPU is to take our frame, that image that we give it, and it makes sure that it appears on the screen, okay? So cool. So we don't have to worry about anything after we've generated this image. We just need to generate that like actual set of pixels, right? So how might WebKit go about doing this process of rendering? Well, a very simple and naive approach, we'll go through in a second with a simple example to see how we could do it just in a very simple sense. So let's consider a very simple system where we have, say, a small screen, and we have a very simple page. And so the page is about 20 by 20 pixels. And on the body, we just basically have one color, so one big color background. We have one child that's this square div, and it's just 10 by 10. And it has one background color, right, pink. So these like simple squares going on here. And then within the square, there's like a bunch of like little divs. We'll just call them little JS divs. You'll see in a second that are all just a bunch of little white pixels essentially. And it's going to look something like this. So so we have that background square, and then it's cyan, and then cyan, and then we have this pink one, and then the white dots. So how might we go about like creating this, right? If we were just given that DOM and we need to make it into this. Well, the first step may be to go through and paint from back to front. So we would basically fill in the pixels of this like frame thing, right, this image, one by one, where we put in blue, 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 and then eventually extrapolate and go fill out the whole thing. And the next step that we could do is to go to that next child element, that second div, that square that's pink, and we fill in, just fill in the pixels, boom, 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 the values and the whole thing. Recurse again to the children, and we go through and we fill in all for the J and the S. And that's pretty simple, right? So that's essentially what boils down to the process of rendering. That's a pretty simple, naive approach of how to do it. So let's think about for a second like how many operations we were doing to do it in this naive approach. Basically, we had that 20 by 20 square, and then a 10 by 10 square, and then 7 by 5 that we did on top of that. So this results in about 535 pixel fill operations. So that's the kind of like amount of time it would take to generate every one of these frames, right? But we know that like the average screen goes about at 60 frames per second. So multiply this out, and we're looking at, for this tiny screen, 32,000 operations to do this per second, right? So for the modern CPU, this is obviously no problem to do. However, if you consider like a much bigger case, you can imagine this can start to get really expensive, right? So like a maybe MacBook Air screen where you have 900 by 1440. Now you're talking about a lot of operations, like just over close to 2 million. So that's simply just the amount of time it takes to fill in these pixels, right? But even worse, oh, so right, so that's the operations per frame, and like overall, you're looking at 102, million per second operations you have to do for that. So if you consider like that an average system is doing a lot more things than just rendering, this is a lot of time to do this naive approach. If you have a lot of different programs going on, different windows, a bunch of tabs open, you're talking about a lot of different people doing this amount of work, and that just becomes too much. It doesn't scale. And if you consider even worse, you're looking at about 600 megabits per second, like for just pushing this one set of frames from your screen over to the GPU, which is just a ton of data transfer, which could just totally bog down the system, right? So basically, this doesn't quite scale, right? This is not a good approach. We can't possibly make fast web pages with this. So in comes the role of compositing, right? So basically, in that first approach there, we were just running through and kind of doing all rendering as like one pass, right? But compositing is this notion of breaking up the step of where you're combining visual elements from separate sources into like one source. So we were kind of doing this implicitly before when we drew from back to front. We did like the one color, the next color over top. We were by the method of drawing, we were actually implicitly compositing appropriately. So instead, let's break this up into two discrete steps, right? So the first one is drawing, and the second one is compositing, like I said. So in order to do this, we need to be able to take every element and give it its own little section of memory that it can do the drawing into initially. And then we'll do the second step that I'll explain in a second, that's compositing, which is the process of combining all of those separate images into this one that we need to give over to the GPU, right? So let's start by looking at it. We had like that. We have the three different, we'll call them layers. So these are basically like the little like off-screen kind of frames per element that we're giving. So our DOM was pretty simple. We had that, the body. We had the little pink layer for that background div, and then we have this JS layer, which is just a bunch of those little divs that were just simply the white dots, right? So what we have here is basically these chunks of memory that we need to draw in as our first step. So we're going to go and fill those in like before, same process. We go through, the cyan dots and then all the pink dots and then the JS ones. And now that we have these layers, we need to do the second step, which is compositing. So this is simply the process of taking the contents of the one layer and copying into the other. And instead of going back to front here, we're doing now front to back. So we take the foremost elements that would be in the front of the page. So the JS in the example here, we take all of those little divs that make up the little JS dots, and we are literally copying those into the pink one, so that we composite it into the pink one in the right location, right? So it's simply just a copy. And then we copy that pink one into the appropriate location. We composite it into the overall body. And now basically the layer of the body finally has the contents inside of it that we need to give over the GPU. So you may be asking yourself, like, what's the point of this? Like, we just allocated a bunch more memory and did just as much work, but we didn't gain anything. But you have to consider what happens when things are happening first at a larger scale. You have a lot of things you're drawing on your page, and perhaps you're even adding effects, like if you scroll, literally the elements are moving around, or you do an effect like you just saw. That's a lot of, if we were to do that repaint every time, we were literally, like in the old method of just simply rendering in one pass, we were redrawing a frame like over and over and over. And I said before, 600 megabits per second, like throughput to the GPU, all of that. That was a lot of time. So in this compositing path, though, we can instead skip all of that rendering and compositing that we did for that pink layer, and we can just use the contents of that layer and recompose it into different locations in that overall blue layer, right, that topmost layer. So that basically saves us a ton of work every time. We can go a bit faster here. So there are obviously trade-offs. We have allocated a bunch more memory to get some speed-ups in how we do things. So of course, memory is not limitless. You definitely have a kind of a trade-off of how many layers you should be allocating, depending upon how much performance you need, perhaps, to like speed up the rendering. So it's important to remember this. Now keep in mind, at this point in the talk, we haven't yet talked about hardware versus software. We basically, everything we've been doing to like do this rendering and this compositing and this drawing has all been happening. You could just do it in software. Like any program could do this, right? So now it's interesting to consider how might we use the hardware to speed up some of this stuff. Well, first, like, let's think about like what's slow here, right? So CPU rendering takes a lot of time. That's what we were just doing, just in software, just filling in those pixels, right, as we know them. That's a ton of operations, right? And the second part was it's really expensive to eventually take that product and push it over to the GPU. That's just, like, copies are really expensive to go to the GPU. So we want to minimize those things altogether, right? So luckily, if you look at any like graphics hardware, you always see like that there's some sort of amount of megabytes that the card has. Well, that's its GPU's memory, right? So what's the point of this memory? Like, how could we use this here? Well, if you think back to our process of doing the drawing and the layers and then compositing step, that compositing step had a bunch of these just chunks of memory, these layers that we've generated, and they're not really changing, they're kind of just there. So what if we instead copy them over to the GPU's memory? So we say, hey, GPU, hold on to these, right? We've just drawn these, cool. So we draw them once and give them to them, and then so all we need at this point to basically finish the process is if we just had a way to tell the GPU, hey, take these layers, right, and squish them together because that's like the last step, right? Well, luckily, this is exactly what GPUs are designed to do incredibly well, right? So these textures that we have on the GPU acts like a compositor for us because we give them the simple lightweight commands on any given frame that we're drawing to make, like, say, our animation around the screen or scrolling. We're saying, hey, take those layers and rearrange, like recomposite that pink one to be on the blue one in this next location, next location, next location. That kind of communication is really fast. Copying those frames every time, not fast. So this is something that the GPU is designed for. It's a great sandwich maker. And this is basically, this is accelerated compositing. This is exactly what we do in WebKit. This is the process. So back to translateZ, right? So what's going on here with translateZ? Well, it's doing exactly this. It's kicking us into a mode where we start doing it in the second fashion, where we start allocating these layers for things that you translateZ on, because we can't afford to not handle this 3D case where we need to do it, or else it's just incredibly slow. So we jump into compositing mode. We start allocating layers, those things you give translateZ to, which means that they also start to have all this extra memory, right? So this is kind of like the be careful message, right? This is where you're walking with a really heavy stick when you start translating Z on everything. But of course, you can get really fast speedups if you're doing the kind of thing that would basically be draw once in a layer and move it around the page, because that hardware compositing is what works really fast, right, in this mode. Cool, so let's go back to our example and use a little thing called WebKit debug borders to check out what's going on in our example when we added translateZ. So those words are falling, really sweet from the top. And so now we see that like every single word has this debug border around it. Now I'm not going to go into too much detail about this, but this is basically a little debug mode that we have in WebKit to look at which elements on the page are actually getting these layers. So they're actually getting memory assigned to them that they get to draw into that's reserved for just them, and then is also backed by GPU memory, right? That we use in order to do this accelerated compositing last step. So obviously you can see there's like plenty of things in the page that are getting these little green boxes. However, we're doing this well because we're not overusing them. There's nothing in the page that's like getting these layers that doesn't need it to, like all the words in the background, for example. So this is a perfect example of how to use it correctly. And yeah, so we're about at the end of the talk here. And so just as like one more point, right, is if I guess for fun, if you consider like ways to minimize the usage of it and use it just for the kind of cases where you're doing those things that would benefit from accelerating the compositing, then you could even get like really nice effects like this in a page. So we kind of made a different version of the game where it's just really taxing a lot of things being moved around. And we have a little bit of time left. So that was a quick run through of how accelerated compositing works in WebKit and how rendering in general works in a browser. Does anyone have any questions?
So The other browsers don't have this problem. Why does WebKit have this problem where they need to create new layers for every hardware accelerated thing?
Which problem?
The other browsers like have one layer and they hardware accelerate everything on that, at least according to their tech docs.
Well, right. They may be accelerating like the actual like body that all the time, which essentially is kind of always the case because you always need to have some sort of reserved chunk of memory that you eventually draw into. The idea is if you are using intermediary chunks of memory, right, like little buffers along the way to do part of the drawing into, which anyone does when they're doing this compositing, right? It's when you choose to do it is perhaps what's interesting. So it's not that WebKit has a problem, it's the thing that solves the problem of doing it faster. Yeah, if that makes any sense.
So you showed the example where you're accidentally triggering the whole reflow in the loop. How can you tell that you're doing that, or how can you? Is there sort of way to see that that's happening? You know, all you can see is the performance sucks. But
right. Yeah. So of course you can always like try to be cognizant of that, but at the end of the day, like when you're debugging, the biggest tip is to go into the web inspector and look at timelines. Maybe you want to talk about this a bit.
Yeah, so in the web inspector, you can look at the timeline of layout and rendering. And when you're triggering all this reflow, what you can see is a lot of like relayout, 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 relayout in between two renders. So you really ideally only want to do one relayout before one render. Another good way for this specific case is that you can actually find this online. I think several people have talked about it or blogged about it. They listed all the values that would trigger this relayout. And they're called computed values in WebKit. And if you look for the earlier function I showed, like update layout, ignoring blah, 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 if you search for that, then that pretty much lists out everything that you need to be cognizant of not using too much.
All right. I think we're out of time. We're going to have a break now and come back in 10 minutes. So thank you, guys.